Hello there. In this video, we're going to work through the process of solving triangular systems using back substitution in a numerical fashion. So we're going to pretty much be looking at matrices of the form or systems of the form. Let x's be non-zero values. So an upper triangular system would have a structure such as this, right? And let's assume these x's are not equal to 0, right? But they can be, I don't really care. As long as these diagonal entries are non-zero, so uij is not equal to 0 for all I. That's at least a requirement that we're going to need for this problem, right? So we're going to go through the process, derive an algorithm, and then we're going to go to MATLAB and try and code that up. All right, so let's sort of go through the process of how we would solve a triangular system, and then we can sort of get an idea of how we can construct an algorithm, and then we're going to go to MATLAB and code that up. All right, so let's consider an arbitrary upper triangular matrix, let's say 3 by 3, and then we can extend it to higher dimensions if we need. And then we have A11, A12, A13, 0, A22, A23, 0, 0, A3, 3. Right? And we're going to take this matrix and we're going to be multiplying that by the column vector x1, x2, x3. That's what we're solving for. And let's assume that's equal to some other column vector b1, b2, b3. Right? And of course this is associated to the standard system. So it's very easy to see how we can solve this last equation, right? So we can divide both sides by a33. So we have x3 is equal to 1 over a33 of b3. Right? So that's the solution to the last equation, which is going to be the general structure of xn is equal to 1 over a n times bn, right? So that's trivially what the last, or the first step, is actually going to be, right? So then we're going to solve this second row part of this equation. So what does that equation look like? So that's a22x2 plus a23x3 is equal to b3. So we can isolate this equation for x2. So if x2 is going to be equal to 1 over a22 times, so b3 is always going to lead minus this expression here. So that's a23 x3. Right? So that's the structure. So it's very easy to see that this leading term is always going to match whatever index we're at, right? That's easy to see. And let's go to the first equation, which is a11x1 plus a12x2 plus a13x3 is equal to b3. So as usual, we're going to isolate this equation for x1. So we have x1 is equal to what? So a11 times, we're leading with b3 here. It should be b1. Why is that 3 there? So we have b3 minus this term. So a12x2 plus a13x3, right? All right, so let's try and derive a pattern here. So clearly this index matches this, that, and that, right? Why is that 3 there again? That 3 keeps on sneaking up. All right, so, and what's going on here? So these two are the same, and these 3 are the same. And keep in mind that's n, right? So if we call this number, say, k, then we have that xk is going to be equal to 1 over a kk times bk minus the sum, and then we can create some new index variable. So L is equal to, so this is 1 higher than that, so it's going to be k plus 1 up to n of a k l xl. Right? So that's the general strategy. And of course, that's step 2 because you need to start this process off. The first step, of course, is going to be xn is equal to 1 over ann times bn. And this loop, right, k is going to start at n minus 1, then go to n minus 2, and that's going to finish off at 1, right, in a backwards fashion, right? So let's write this algorithm up. So algorithm. So the first thing we need to check is this matrix upper triangular? If it's not, this code's not going to work. You have to do a more generalized structure, right? So this matrix AN that's going to be inputted to us, we need to check that Aij is equal to 0 for all row numbers that are larger than or equal to the column numbers, right? And this includes both the diagonal and all of the elements underneath that, right? So if this is true, then we proceed. So we define xn to be, well, it's not really defined, but it's pretty much starting the iteration off. So ANN times BM, right? And then we can start the iteration process. So for k is equal to m minus 1, n minus 2, m minus 1, m minus 2, all the way down to 1, we have that xk is 1 over xkk multiplied by, let's use brackets, bk minus the sum from L is equal to k plus 1 to n of AKL XL, right? And then that pretty much gives us the solution, right? So solution is x1, x2 down to xn, right? So that's the algorithm for the back substitution, which is pretty much the ending step for Gaussian elimination, which we'll get to later. So let's get to MATLAB and code this up and see how it works. All right, so let's get started on coding this backward substitution method that is applied to triangular matrices and triangular systems. So I'm just going to begin by cleaning up my disk space just in case you have any figures open or you have anything in the command window, which CLC will delete. And I'm just going to create a matrix A that I'm going to use to sort of pilot this. So I'm going to use the matrix 3 minus 2, 1, 3. And then on the second row I'm going to have 0, 2, 1, negative 2. And then we're going to have 0, 0, 3, minus 5. And finally 0, 0, 0, and minus 7. So this matrix, at least as I have it inputted here, is definitely a triangular matrix, right? And then I'm going to have a column vector B, and I'm going to define it to be 1, minus 1, minus 17, and minus 28. All right, great. So the first thing I need to get is the size of these matrices because I can make it an arbitrary input and not manually define a matrix A and B, right? So M and N is going to be the size of matrix A, and MB, and I don't really care about the number of columns because it should be 1, this should be equal to the size of B. So the first thing I need to test and see is to make sure that this matrix is square and that this column vector has the same exact number of rows as the matrix A has, right? So that's the, so let's do a couple preliminary tests. So tests for input validity, right? So if M is not equal to N, right? So that's the rectangular non-square case, right? So we're going to display an error message. The given matrix A is not square, right? And return will exit this entire function that I have here. If MB is not equal to M, so I'm comparing the number of rows in the matrix to the number of rows in the column, ideally vector, then the rows in A do not match the number of rows in B. The next thing I want to test is whether this matrix is upper triangular. So test for upper triangularity. Right. All right, so let's see here. So I'm going to go through the diagonal entries first. So for k is equal to 1 to n, where n is the number of rows, and at this stage it should be equal to the number of columns. So we're going to check the diagonal entries first. So if a kk is equal to 0, then the diagonal entries are 0, and that's a problem, right? Then 1, or at least 1, of the diagonal entries is 0, and the user should know that that's a problem for the backward substitution method if this is truly a triangular system. Then I'm going to go towards the lower side of the spectrum. So for j is equal to 1, 2, and minus 1, so I is the number of rows and j is the number of columns, I'm going to go first column up to the second to the last column and minus 1, because remember, in the last row nth column that should not be 0, and this should check that. And then we're going to go for I is equal to j plus 1 to n. So why do I start at j plus 1, right? So when we're in the first column, the first row will have a non-zero entry, right? That's on the diagonal, right? So ith row, jth column, 1, 1 has a non-zero entry already, so we need to go to the first column, second row, first column, third row, first column, fourth row, all the way to the first column, nth row, and that's going to be the same for all columns, 1 to n minus 1. That's why we start at j plus 1 and go up to n. Right? All right, and let's make sure that they are non-zero. So if ij is not equal to 0, then we have a non-upper triangular matrix. Right? So the matrix is not upper triangular, and this program will not work. Right? So up to this stage, everything should work well. Right? So that's great. Right? So let's put a little smiley face there. Smiley face. Okay, cool. All right, so now let us create a vector that is going to store our solution. So x is going to be the same dimensions as our vector b. So let's create a space, n rows by 1 column, column vector. And let's start off the process by defining the last one, which we should already know. So xn1 is going to be the reciprocal of a nn times bn1. bn1, right? So that's the start of our procedure for the backward substitution iteration method. All right, then we're going to go from k is equal to n minus 1 down to 1. So that means we're going to subtract 1 each time, right? So n minus 1 to 1, subtract 1 each time, right? And then we're going to have a sum inside of each of these things. So we need to do a quick sum loop. So sum is equal to 0. So for L, so that's our index for our summation. So L is going to start off at k plus 1 and go all the way up to n. So sum is going to be equal to sum plus, oh, where'd my stuff go? Oh, there we go. So sum plus, so we have a kl, right? Kth row, lth column, times then the previous x value. So that's lth row, 1 column. Right? And then we're going to take that sum, and then we're going to calculate our x value. So x k1 is going to be equal to 1 divided by a kk, that's the diagonal entry, times b k1 minus that sum value. Right? And that's going to go through all of the rows from n minus 1 all the way down to 1, and then our system should be completed. So then we can display our x value, and then that is fine. So let's just give this a test go. Let's make this matrix non-triangular, so let's make this diagonal entry 0. So at least one of the diagonal entries is 0, so that's safe, that checks out. Let's make this non-zero just to make sure that works. The matrix is not upper triangular, so that works. Let's create another row. So 5, 5, 5, 5, right? So that creates a non-square matrix. All right, so that checks out. And let's make this not the same size, so 4. So the rows in A do not match the rows in B. So we should have a return statement here so it doesn't continue onwards. Okay, great. All right, so that checks out. So everything's working fine so far. So we start off with the system and we get this vector here, right? So let's just quickly define these two vectors A and B. So A and B is that. And let's let X be equal to this vector that it inputted, and let's just make it true. So -2, 3, 1, 4, just to verify that this actually is working, right? So what is A times X equal to? Is that equal to B? Yes, it is. So you can do like A times X minus B, and you should get the 0 vector if those are indeed equal, right? So that's just a quick MATLAB implementation of how to solve and check validity for upper triangular systems and how to use back substitution to solve them. We're going to use this later for the Gaussian elimination function. Hope you enjoyed.